Let us look now at fluids in motion. So the first type of fluids that we will consider are ideal fluids. Ideal fluids don't actually exist unless we're talking about superfluids, but that's beyond the purpose of this course. So characteristics of ideal fluids are incompressibility, so they can't be compressed. They're non-viscous, which means that they have no resistance to flow. They don't stick to the sides of the vessel that they're traveling through. And they have laminar or non-turbulent flow. Laminar flow means that it's a nice uniform steady flow, and we can approximate it with various layers of that fluid traveling constantly parallel to one another. So one thing that we'll have to consider is the volume flow rate, which is the volume of fluid that passes through an amount of time, and that volume flow rate will be constant. So let's say that we have a situation like this where there is some sort of constriction in a pipe, and let's say that this cross-sectional area is A1, and through here the cross-sectional area is A2, then velocity V1 will be the velocity of this area of the fluid A1. Velocity 2 is velocity through the constriction. So in order to keep these two quantities equal, we see that if A1 is large, V1 has to be small so that the flip side occurs in A2. So A2 is small and V1 is large. So we have an inverse proportionality between area and velocity. So where area is large, velocity is small. Where the cross-sectional area is small, the velocity is large. So there is one equation that we can apply for the ideal fluids in motion, and it is pretty much the conservation of energy in fluids. So let's say that we also have here a pipe, and it rises up like that. So if there is a portion of the fluid that is pushed with pressure 1 here, at this other location there will be a pressure 2. And let's say that we're measuring the height of these columns of fluid from some common zero, some common ground, and call these H1 and H2. Then there will be a velocity, so this thing is flowing with velocity V1 down here and velocity V2 up there. So what Bernoulli's equation says is that the pressure P1 here plus a potential energy type term, the density of the fluid times G times the height, so the potential energy of the fluid at this location, plus here we have a kinetic energy-like term, 1/2 times the density of the fluid times the velocity squared, is going to be constant. So that means that it's going to be equal to the pressure up here plus the potential energy-like term due to height 2 plus the kinetic energy-like term, which is 1/2 density times the velocity 2 squared. So let's look at a different case of this where we have the pipe staying at the same same vertical height. So when we measure H1 and H2 in these two situations, then we see that those are the same. So then in Bernoulli's equation, we can just cross out these terms. So now we're comparing pressure 1 with pressure 2 versus velocity 1 and velocity 2. So like we had with the volume flow rates, we said that if we want to keep this quantity equal to that quantity, if pressure 1 goes up, then on one side of the equation, then velocity 2 goes up on the other side of the equation, because then we'll have to have velocity 1 be small and pressure 2 be small. So to keep these, it's not a multiplication, it's just the different terms. So what we're trying to say here is that pressure, high pressure corresponds to low velocity and the other way around. It is a little bit counterintuitive, but it is the case given to us by Bernoulli's equation. So remember again that from the volume flow rate equation, we had high velocity went with low cross-sectional area, and high velocity also goes with low pressure. And the other way around. So low velocity is in a high cross-sectional area, and that low velocity also has to do with high pressure. All right, so this is what I summarized here. We have low velocity and high area multiplied together will be equal to high velocity times low cross-sectional area, and here we have high pressure that corresponds to low velocity and low pressure corresponding to high velocity. So one application of this is the Venturi flow meter. It's not necessarily an application, it's a meter. It's measuring different pressures in different parts of a pipe. So let's see how we can do this. So let's say that there is a pipe with a constriction in it like this. And let's say that we have some tubes that stick out of these pipes. So there is an opening in there. So there's a tube here, and there is a tube over there. And we know that there is, I guess I can erase this a little bit so that we can see that there is contact here between the tube, so the fluid can flow into the tube here and at that location. So I'm going to make the fluid red. Let's say that we have fluid going this way and then back out, and here it's going to be closer together and so on. So I'm drawing a laminar flow. The different layers of the fluid are going to flow as parallel lines. All right, so if this is cross-sectional area A1, this would be cross-sectional area A2, and in area A1 there will be pressure 1, in area 2 there will be pressure 2, and the fluid will flow with velocity V1 in area 1 and with velocity V2 in area 2. So based on experiment, it was observed that the fluid rises in the first pipe higher than in the second pipe, and that height difference is h, and it has to do with the fact that the pressure in pipe 2 is lower than the pressure in pipe 1. So the fluid rises to a higher level here than there because the pressure 1 is higher than pressure 2. And again, pressure 2 occurs where there is a constriction, so there's a lower area and the fluid will have a higher velocity. All right, well, let's look now at real fluids. So unlike ideal fluids, real fluids are viscous, so they have a resistance to flow, and they can have laminar or turbulent flow. So viscosity, the symbol for that is the letter eta, is a fluid's resistance to flow. So we can talk about the viscous drag, which is a non-conservative force, just like the air resistance is a non-conservative force. Laminar flow, we talked about it a little bit before, is orderly and smooth and can be thought of as layers of the fluid flowing parallel to one another. Poiseuille's law describes the flow rate, and that flow rate is Q, just like we had Q over here, volume per time, is equal to pi radius of the tube to the 4th power times the change in pressure divided by 8 eta, which is viscosity, times the length of the pipe. So again, the volume flow rate is pi times radius of the pipe to the 4th power times the difference in pressure, or the pressure gradient, divided by 8 times the viscosity of the fluid times the length of the pipe. So one thing that we need to note here is that the volume flow rate is proportional to the radius to the 4th and the pressure, which means the change in pressure, which means that the change in pressure is inversely proportional to the 4th power of the radius of the pipe that the fluid flows through. So that is an important thing that we need to remember when we're dealing with viscosity, that the change in pressure is inversely proportional to the radius of the pipe to the 4th power. Turbulent flow is non-uniform. There are swirls of fluid called eddies that form throughout the liquid, generally past an obstruction in a pipe. So if we have a pipe and there is some sort of a blockage, when fluid comes through, it comes and goes past here and swirls around. So these are what we call eddies in the turbulent flow. So in turbulent flow, Bernoulli's equation no longer applies, but turbulence can arise when the speed of the fluid exceeds some sort of critical speed. So this critical speed is given by a quantity called Reynolds number, the viscosity of the fluid divided by the density of the fluid and the diameter of the pipe the fluid is flowing through. So this Reynolds number is a dimensionless constant, and it depends on the size and the shape and the roughness of the surface of the object that is obstructing the fluid.